Okay, this is chapter 6, day 2. Very long chapter, probability. This used to be 2 separate chapters and it was combined in later editions, so that's okay. This is a really great chapter. We're talking about discrete and continuous random variables again. As I said, as you probably heard me say, discrete's a funny word, has many meanings. Meaning one of discrete is like be quiet or be secretive, but the math meaning is very different. A countable number of outcomes, countable number of outcomes. And continuous random variable, continuous, means any answer is possible. An infinite number of answers are possible, even within a certain area. The one I always think of is when you're driving on the freeway, everyone's driving between 60 and 80, but no one's going the same speed. It's a continuous variable because there's so many decibels. I'm going 75.4356 miles per hour. There's just an infinite number of variables on that. Height is another one. Everybody's a slightly different height if you go out to enough decimal places. Okay. So discrete is countable, continuous is like the normal curve. Is one example of a continuous variable. I have 2 of them sitting here, of course. This is a skewed right curve, and this is a normal curve, but it's still a continuous variable, okay? By the way, the mean or mu is the balancing point. If it's the normal curve, it's the middle. If it's something like this, of course, it's a little bit not quite the middle, it's the balancing point. And then you got standard deviation, we know all that stuff. So if it's a normal curve, of course, you can take the maximum and minimum and divide by 6 and you'll get about the standard deviation. Remember that club called 6 sigma? That's where that comes from, because there's about 6 standard deviations about in a normal curve, 3 to the right of the mean and 3 to the left of the mean, okay? When you get into discrete variables, I went a little backwards there, how you calculate the mean is this formula. That's a weird looking formula, but what that means is x sub I means every individual x multiplied by the individual probability, and then you add it up. You're going to see me do an example of this. It's actually very easy, a little tedious, but very easy. And the standard deviation for a discrete random variable is every individual number minus the mean squared divided by its individual probability square rooted. Again, it can be very, very long to do, but I'll do this and you won't find it difficult. It's just a little annoying. Okay. All right. So let's give this a try. Okay. Let's go down here to determine whether discrete or continuous random variables will be utilized. All right, a digital clock, that's when it says late. That's what we have in the classroom, 10:42. That is discrete because it doesn't show you seconds or fractions of a minute. And then continuous would be an analog clock. An analog clock is one with a hand that goes around. You can have any time there you want. Okay, 1B, you got feet size. Feet size is continuous. Everybody's foot is slightly different. But shoe sizes, unless you get them custom made, they only come in halves. 5.5, 6.5, 7.5, 8.5. There's no 3/4 shoe. I know the metric has a little bit more variety, but it's still discrete. Okay, and then C, difference in race times. Let's say a cross-country race. That's continuous because seconds can really, you can go out to the hundreds or 10 100ths or whatever you can do. Okay. And then basketball scores is discrete. There's no fractional scores in basketball. So, you can only lose by 1, 2, 3, 4, whatever it is. There's no fractions. While race times, you definitely have fractions, like swimming times or track times or whatever. Okay. So that's discrete and continuous. Okay. Item 2, calculate the mean and standard deviation. All right. The mean. And what we're going to do here is we're going to see, I can get this all, make this a little bit smaller and get it all in there. Cool. Okay. Now, what we're going to do on this is we're going to talk about a discrete random, a continuous random variable. Okay. So if you have 2 means that you want to combine in a continuous variable, you simply add them. add the first mean and the second mean. If you want to combine standard deviations of two individual items, it's actually the Pythagorean theorem. This is cool. Do you recognize this as the Pythagorean theorem? Because it is. I find this absolutely amazing. So let me give you a quick example that's not even on here. Let's go through this real quick. So let's say I'm a golfer, okay? I'm a golfer, and I average a 72, which is par, which is very good. And my buddy averages a 70. He's a little better than me because golf low score wins. My standard deviation is 3. His standard deviation is 4, meaning I'm a little more consistent than him. So 68% of the time, this is a normal curve, I would score between 69 and 75, if you remember the empirical rule. Now, combined, if we were to combine our scores, we will average 144 combined. And our standard deviation will be, it's not 7. You don't add them. You do the Pythagorean theorem. It's 5. That's a 3, 4, 5 triangle. So that's pretty cool. So the mean of them combined will be just the summation of them. But the standard deviation when you combine two continuous random variables is the Pythagorean theorem. Now, if you have 3 items or 4 items, it's still the Pythagorean theorem. It's just squaring them all, adding them up, and re-square rooting them. Okay, I think that is so cool, and is one of those beauty of math things. I think it is so amazing that the Pythagorean theorem explains variability as well when you combine things. I think that's really cool. It's not just for triangles, it explains variability. So that's really cool. So now we're going to do a couple of problems on this, and you're probably going to want to pause this video and do them by yourself at first. I'll be drawing some of them and showing the answers as well, and you'll be using your calculator, and I may have to break mine out just to review it for you. Okay, this is something from chapter 2 as well. This is in addition to chapter 2. Okay, so we got swim times in the 100 meters. I don't really know swimming, so I made up these times. We got Jennifer and Michael. Jennifer's swim time is 95 seconds with a standard deviation of 5, while Michael's swim time is 100, standard deviation of 10. I don't know if that's a slow or fast. I don't know if these kids are 5 years old or 30. I just made it up. Okay. So who has a better chance to swim under 87 seconds? Under 87. All right. So what you're going to do in this case is we're going to draw 2 normal curves. And I would highly suggest you do this. Remember, we've done this a lot. Raw score, z-score, percentile. We've done this a ton, and I've been coaching you to draw this type of map here. Okay, so here's Jennifer. She's at 95. Standard deviation is 5. Michael is at 100. He's typically slower, but a standard deviation of 10, which means he can go really slow or really fast. He's very inconsistent. Probably doesn't try very hard. Okay. Now, Jennifer's swim time, they want under 87. Okay. So 87 is somewhere out here. All right. Now, to do the z-score on that, I've done it right here. 87 minus 95 divided by 5 is negative 1.6. Okay. And then for Michael to do 87, he's going to do 87 minus 100 divided by 10. So it's negative 1.3. Okay. So negative 1.3 is going to have more likely to occur than negative 1.6. Okay. So you can actually stop at the z-score comparison. We've done that in the past, where negative 1.3 has more area to the left of it, because under means to the left, than the 1.61. Now, if you wanted to finish this problem out, we can very, very easily. Let me bring up the calculator. One is negative 1.3 and one is negative 1.7. Hopefully this will pop up here in a second. Okay. So here we go. So I'm going to go second distribution NCDF, and I'm going to type in negative infinity, which I just do this, and the upper bound is negative 1.6. Okay. And then that's good. Different calculators do it differently. And you get about 0.0548. So 0.0548 for that one. And then on the other one, we'll clear this. Again, hopefully you remember how to do this from the past. Second distribution NCDF, negative infinity, negative 1.3. Okay. 0.0968. 0.0968. Okay. Let me minimize this. We'll get this back on the screen there. Boom, boom. So as you can see, Michael's got about a 9.68% chance of swimming under 87 seconds, while Jennifer has about a 5.48% chance of swimming under 87 seconds. What's ironic is Jennifer is better overall. She's quicker because we want a low score. 95 seconds compared to 100. She's typically 5 seconds better. But because Michael is so inconsistent at his standard deviation is double Jennifer's, that he actually has a better chance of doing really good. He also has a better chance of doing very poorly. So that's kind of a cool prompt. All right, so let's go to B, okay? And I got those numbers down here, okay? So let's go to B. B is really easy. It says, what is the probability of something back-to-back 87 seconds? Now, I want to make a note here. It doesn't say this. So back-to-back means you got to do it the first time and the second time. And means multiply. So it's right here. You're going to take both people and square it, because Jennifer does the 5.48% chance twice in a row, one and the other. So the best answer is this, and you write this: assuming races are independent. I would like you to write that down too, assuming races are independent, because you multiplied them together, making that assumption. The problem doesn't say they're independent. And if you give an answer that multiplies them together, then you need to tell the reader, this is true, assuming independent races. Because, you know, if people are improving, they wouldn't be independent. Okay, so that's a pretty easy problem. I showed you the calculator keystrokes here, okay, as a review, so it's all there. Okay, all right, very cool. Okay, in a 200-meter relay, part C, what is the probability of swimming under 185 seconds? All right, so in the 200-meter relay, what we're going to do is we're going to add up their times, okay? So typically, in the 200-meter relay, their mean is going to be 195. I got that just by adding, okay? And then we want it under 185. So 185 is somewhere here, right? 185. Okay. Now, the standard deviation is not going to be 15. It's not 10 plus 5. Like I said, it's Pythagorean. So it's actually going to be 10 squared plus 5 squared, which I believe is like 11.18. You can check that on me, 11.18. Okay, very cool. So now what we're going to do is we're going to get the z-score for 185 using the new number. So it's just like a problem from chapter 2. So here's the z-score. Okay, I calculated that. 185 minus 195 divided by 11.18. The z-score is about negative 0.89. I went to 4 decimal places. You don't have to, negative 0.89. And then here's your calculator keystrokes, which I will not do because I just got done doing it. So it's going to be negative 0.89 about, and then it's about 0.1856. So there's about an 18% chance of those two combined swimming under 185 seconds. Okay, so when you combine when you combine continuous random variables, you can add or subtract their means to get that. But when you combine the deviations, you use the Pythagorean theorem. Okay, very cool. So there's that. It's really quite simple. All right. Now that is the one more. I'm sorry, one more. This is the one that's I nickname it the head-to-head one. Okay, so I often call this head-to-head. They're competing. These are really common, these head-to-head ones. Okay, what are the chances Michael beats Jennifer? And then be careful. Note the faster time is the lesser time is faster. All right. Now, a couple of ways to do it. This is the way I would do it. Okay, this is the way, and I do it a little differently here. But draw this curve out. Okay. What I always do is say, all right, what is typical? Just simply subtract their numbers, and put it in a positive number. So the typical number is 5. Jennifer is typically 5 seconds better than Michael. Is that right? It's 90 to 100. Typically is 5 seconds better than Michael. Okay. So with that in mind, that they're 5 seconds better, what we're going to do then is I'm going to put 0 somewhere. 0, I'm going to put it right about here. Whoops. Not in draw mode. 0 right about here. Now, what 0 represents is a tie, because if they both swim, let's say 97 seconds, then they tied. Okay, 0 is a tie. Now, this is how I do this. I always put the difference between their numbers in a positive number here. Then I put the 0 to the left of it somewhere. Then I label each side by name, who gets each side. Who's better? Jennifer is better. She's better because she has a better time. Again, swimming, the small time is better. So I'm going to label this side as Jennifer, because Jennifer is better, and the better performer is more likely to win. And more likely to win means you get more area. You get the area to the right. And then Michael is right here. And I'll put Mike. Mike is right there. Okay, he gets that side. Okay. Now, we're going to go ahead and get a z-score for this. And the z-score is going to be, and I'll write it right here, 0 minus 5 divided by 11.18. Now, of note, when you combine standard deviations for a continuous random variable, you always use the Pythagorean theorem. If you subtract the numbers, because it's a head-to-head problem, the deviation still increases. It's still the same thing. So 0 minus 5 divided by 11.18 is about, is going to be negative 0.4472 or negative 0.45. It's about negative 0.45. Okay, so that's this right here. Now, Michael wins in this area. I'm going to shade it. So I'm going to do NCDF negative infinity, comma, negative 0.45. And I'm going to circle this number in a different color. Let me grab a color for you. I'm going to go purple right here. The answer is going to be about that, depending on what you do. Now, I did this part a little differently. I did it with I did it with like a reflection with a negative number. I don't think I would do that generally. I always like to put the difference between the competitors in a positive number. I always put 0 to the left, and then I label the people. Who's better gets to the right, who's weaker gets to the left, and then I answer the question. Okay? It's a cool prompt, very cool prompt. Okay. Now we're going to flip over to discrete random variables. Discrete is a countable number of outcomes. Okay? And we're going to start, make this a little bit bigger. There, that's really big. we're going to start with the NHL goals. This is data from 2010. There were 1,319 games played in the National Hockey League regular season. Imagine selecting one of these games at random and then randomly selecting one of the two teams that played in the game, one of the two teams. So define the random variable, the number of goals scored by a random team. All right, so the table below gives the distribution. So this distribution has 10 numbers. And the most common number of goals scored by a single team was like 2 or 3, right? 0.228 and 0.229. Very rarely did they score 0, or 9 is very rare. Never, hardly ever happens. Okay. All right. So the first thing it says, show that the probability distribution is legitimate. No problem. To show this is legit, all you're going to do is add these up to make sure they make 1. And they do. So you can trust me on that, or you can sit there and add them up. No problem. Okay. All right. The next question. The next one is make a histogram for what you see. All right. Histogram, no problem. So on this, all we're going to do is just draw a little histogram. So 0 is 6% of the time. So I'm going to go right there. That's a bar anyways. 1 is 15%, no problem. It went a little high there, but 2 is 28%. So that's right around there. 3 is 22. Let me erase just a little bit here. You try this all over again. I don't like how I did that. 6%, 15, about 15. There we go. About 22 or 23. There we go. About 20, same thing, somewhere in there. 4 is 17. 5 is 9. 6 is 4. 7 is 1. 8 and 9. All right, so this is pretty classic, skewed to the right. Okay, there we go. That's better. And then describe what you see. All right, remember that's cuss. Okay. All right. So I did see what I wrote down here. Let me slide this up just a little bit. I did the median of the distribution is 3, and the mean is 2.932. That's C part D. There doesn't appear to be any unusual gaps or outliers. The distribution is skewed to the right, and the range is 9. I did my cuss acronym again. That's a review from chapter 1. Remember that chapter 1? How we talk about that? Okay. So there we go. So you can see that. All right. Okay. So again, pause the video and write that down. That's a review from chapter 1. Very common question. Describe the distribution. We know that that's a common question. All right. Now, question C, what is the probability that the number of goals scored by a team in a randomly selected game is at least 6? At least 6 and more than 6 are different questions, right? Now, this is important to make a note of this. You might want to listen to this. At least 6 and more than 6 are different questions in a discrete random variable. It is the same question in a continuous curve. In a continuous curve, at least 6 and more than 6 is the same thing because we don't differentiate because it's a continuous curve. So in a normal curve, that's the same question. In a discrete curve, it's different. So at least 6, more than 6, no problem. And I'll get it up here. At least 6 is 6 or more. So it's adding these 4 up. More than 6, of course, is the one in red right here. These 3 added up. At least 6, more than 6. Again, those are different questions in a discrete variable with like a chart, but it is the same question in a continuous random variable. All right. And you see the math here. Okay, more than 6 is, you can add those up there. More than 6. You see the math there. Okay, no problem. Now, item D, what is the mean of the distribution? Interpret the meaning. All right, I'm going to get to this in a second here, but how do you do the mean? And there's a formula that we had up there. Okay, the formula is way back up here. Okay, it was this one. and I'll circle it for you at the beginning here. It was every individual X multiplied by every individual probability added up. That was the mean of a discrete random variable. No problem. So let me show you on this. So the mean of this particular problem is going to be, watch my arrows, 0 times 0.0061 plus 1 times 0.154 plus 2 times 0.228 plus 3 times 0.229 plus 4 times 0.173 plus 5 times 0.094 plus 6 times 0.041 plus 7 times 0.015 plus 8 times 0.004 plus 9 times 0.001. Wow. Now, usually on the AP test, they don't give you a chart with 10 items. They give you like 3 or 4, so it's a lot easier. This is overkill, okay? So that's the mean, and I'm gonna slide down so you can see it. That's this one, it's item D that we're on right here. It's right here, we're on D. And that's those numbers, 10 items, and it ends up being about 0.2851. And what does that mean? On average, we expect a randomly selected team to score about 2.85 goals a game. That is the average, okay? So again, pause the video and go ahead and do that. The next one is, what is the standard deviation? Interpret the meaning. This problem is awful. It's not hard, but because I have 10 items, it's super long. And this is the answer right here. Okay, I'm gonna go ahead and slide back to the top, and I'm gonna do it. I need to see the chart. So I'm gonna go ahead and do it. I'm gonna write it out, and you can write the whole thing out. It's very, very long. But again, most of the time, you're gonna be given just 3 or 4 items in a set, so it won't be that much. So the mean is 2.851. So let me slide back up here and do, look, this is a massive problem here. So I'm going to do the standard deviation right here. Sigma equals, hopefully I can fit. Check this out, this giant standard deviation. Okay. I'm going to go 0 minus 2.851. Let me double check if that was the number. I forgot already. 2.851. Yes, 2.851. I got it. Okay, that was good. 2.851 squared times 0.061 plus 1 minus 2.851 squared times 0.154. Wow. Plus, I'm going to run out of room and I'll stop doing it. Plus 2 minus 2.851 squared times 0.228. I'm going to put ... I got to do 7 more, all those as well. It's massive, but you know, it's doable, especially in a smaller set. On the AP test, they would never give you 10 items. It would just waste your time. They wouldn't do that. So anyhow, you can go ahead and finish that off, or you can just trust me what the answer is in this particular case. Okay, so let me slide down and get that for you. It ends up being 1.6324, okay? So what does that mean? The typical number scored away from 2.854 is 1.632. So even though that's the average, it varies from that on average by 1.6. Okay. Now, I really like F. What's the median? What does it mean? I've seen this question, this right here, what's the median of the distribution? It's really easy to do, but if you're not trained on it, you won't pick it up. So what's the median of this? Okay, so the median of this, what you're going to do is you're going to go to the distribution and you're going to keep adding these numbers until you cross the 50% mark. So as you add 6% and 15%, the first two, you get about 21%, plus 23%, 21 and 23 is 44%. And finally, on the 3, you cross 50%. So one of the threes is going to be the 50% mark. So that's why the median is 3. Okay. So that's pretty cool. Awesome. So that is nearly, that's pretty much the notes on that for chapter 6, day 2. Now listen, I'm going to do a bonus thing for you. Okay. So what I want you to do is just turn your paper over or do something like that. And I'm going to show you something. I'm going to go back over a discrete random variable for a mean and a median, and I'm going to do all that stuff for you. And I'm going to show you some cool things that'll help you. Okay. So just get a blank piece of paper out or flip something over, and I'm going to show you something. All right. Okay. I got a prompt here, and I'm going to go back over a discrete random variable. I'm going to do it a little differently just for teachability here. Just a little extra problem that I like to do. So we got Kelly. She's a basketball player, and Kelly goes to the free throw line periodically. And in the games that she's played, she's gone to the free throw line 0 times 20% of the time, once 40% of the time, 30% of the time she's gone twice, and 10% of the time she's gone 3 times. So if you were asked what is the mean of her distribution, the mean is going to be 0 times 0.2 plus 1 times 0.4 plus 2 times 0.3 plus 3 times 0.1. That's going to be the mean. So this obviously makes 0 plus 0.4 plus 0.6 plus 0.3. Okay, 0.4 and 0.6 is 1, plus 3 is 1.3. So her average number of times she goes to the free throw line is 1.3. Now, the standard deviation of this is going to be this, okay? Very long problem. Let me try to get it in here. It's going to be 0 minus 1.3 squared times 0.2, okay? Plus 1 minus 1.3 squared times 0.4 plus 2 minus 1.3 squared times 0.3 plus 3 minus 1.3 squared times 0.1. Okay. Whew. Very, very long problem to do. Let me try to punch that in. Okay. Try to punch this in so I can see it in the bottom there. So it's going to be, I'm going to go 0 minus 1.3 squared times 0.2. Oops. Try that again. A lot of parentheses. 0 minus 1.3 squared times 0.2, right? Plus parentheses 1 minus 1.3 squared times 0.4, right? Plus parentheses 2 minus 1.3 parentheses squared times 0.3 plus parentheses 3 minus 1.3 squared times 0.1. Takes some time to do this, huh? And I'm going to square root that. Second square root, second answer. So it's about 0.9. Okay, so the standard deviation is 0.9 on this. All right, we reduce that. So this is 0.9. All right, so what we got is Kelly shoots an average of 1.3 free throws per game, and her standard deviation is 0.9, meaning she deviates from 0.13 by an average of 0.9. Okay. Now, what's interesting about this prompt is there's another way to do this, especially when it's intense. So some people see this formula and they think to themselves, boy, we learned a different standard deviation formula in chapter 1 or 2, and now we get this one, but it's really not different. It really isn't. It's the exact same formula. It's a hybrid of it. And you should know hybrids, because if you had trig, you understand there's the Pythagorean theorem, and then there's many, many other formulas that break off from it. Okay, and there's proofs that go along with it. If you think about what's going on here, it's pretty simple. This 0 means 20% of the distribution is zeros. That's why it's multiplied by 0.2. 40% of the distribution is going to be ones. That's why this is multiplied by 0.4, etc. So let me show you another cool way of doing this. Okay, so let me bring up the calculator, and this is only practical. This is only really practical when you're dealing with tenths. If you're dealing with hundredths, it's going to be a hassle, but tenths is kind of cool. So I'm going to go stat edit, and I'm going to get a list here. So let me clear these lists. You can see the overlay there. Okay, so let me go ahead and type the distribution in a mythical amount. So this is in tenths, so I'm going to type in 10 numbers. 2 of the numbers should be 0, correct? Because 20% of the distribution, where my arrow is zeros. 4, there should be 4 ones. The reason there should be 4 ones is because 40% of the distribution is ones. Now there should be, let's see here, there should be 3 2s, because 30% of the distribution is 2s. So 3 2s. And there should be 1 3, because 10% of the distribution is 3s. Okay, now I'm going to go second quit, and I'm going to go stat calc, one variable stats. We did this in chapter 1 from L1. Check this out. When you do this, I'll have to circle it for you. I'll get a different color, like a blue here. So here is the mean. The mean is 1.3. We got that. And here is the standard deviation. In this case, you would use sigma, not S, because we're not saying this is a sample. This is the entire distribution. And if you remember, S stands for the standard deviation if you have a sample. It uses n-1. And sigma, this symbol sigma, is when the distribution is from an entire census. And we have the whole distribution of Kelly's games here. So that's pretty cool. Now, the reason why this isn't practical in hundredths is because I doubt you're going to want to type in 100 different numbers, but you could. So that's really cool. Okay, I really like that to show you how that works. So that formula is not a brand new formula. It is a hybrid of the one that we learned earlier. All right, now what's the median of this? Last question, median. Now the median is the 50% mark. So if you wrote these out in order, you would have 2 zeros, you would have 4 ones, 2, 3, 4. You would have 3 2s, 1, 2, 3, and you'd have 1, 3. The median is going to be the middle of the 5th and 6th number. So 1, 2, 3, 4, 5. It's the middle of those two. The average of 1 and 1 is, of course, 1. So the median of this distribution is 1. And the mean is 1.3, meaning this is slightly skewed to the right because the mean is to the right of the median. Now, the other way to do that is to look at these numbers, and when you cross the 50% mark, that is your median. So 20% plus 40% is 60, so it must have crossed with one of the ones. So that makes that the median, okay? Very cool. So that's a little extra problem. I think it's really good for you to do and marinate on. And that's going to end this lesson, and we'll see you next time. Thanks a lot.